So, in this video, I'm going to focus on what we call the inverse of a matrix. And what you're going to see from here onward are some concepts that are all connected to finding the inverse of a matrix. Right? All these are just the concepts might seem disjoint. You want to know what is all of this about, but they're all connected to what we call inverse of a matrix. So basically, the inverse of any matrix, and not all matrices have inverses, um, right? Usually, there's something called a determinant that you have to find to determine whether the matrix has an inverse. But the whole idea is this: you take two matrices and you multiply them, and you get what we call the identity matrix. Again, this matrix and this matrix are the inverse of one another, right? This is the inverse of that, and that is the inverse of that. And if you do the same here, if you multiply b by a, you'll get back I there, right? It's one of those times when commutativity actually works. So everything you see from here onward is going to be directly or directly related to the inverse of the matrix. I just want to mention that at the beginning. As long as you want to know, why am I showing you all these things? They're all connected to the inverse or finding the inverse of a matrix. So the first thing you want to learn is how to transpose a matrix, right? And what transposing a matrix actually involves is switching the rows into columns, right? So here you have a matrix. These are the rows. Watch it. These are the rows here. And all you do, you take these three, right? This row here and make it into a column. You take this row here, make it into a column. That's all. It is simply taking the rows, making them into columns. Right? And of course, if you transpose back this, you'll go back that, right? That's what the transpose of a matrix really means. You are interchanging the rows with the columns. You are making the rows into the columns. Very useful. This is part of when you go on. Later on, you're here, you find the cofactor matrix, and you're going to take that cofactor matrix and you're going to transpose it to get what we call the adjoint matrix. You're going to hear about, we're going to see all of that as we go along. Just tell you where all of this is headed. Right? Good. So another example, right? This is another example, or is it the same one? Right? Notice here. All right, another here. The rows become the columns, columns become the rows. How does that? Right? So you see this row becomes first row becomes first column. Second row becomes second column. I think that should be on. And these are some additional properties. They're not connected with the inverse, right? These are just some general properties. It's telling you if you were to add two matrices, then transpose it, it's equal to if you transpose the first one, transpose the second one, add them. Second one, notice the second one. If you multiply two matrices, then transpose them. It's the same as if you transpose each one of them individually and then multiply them. You get the same answer. These are just trends people observe, mathematicians observe. No? Here, if you multiply a constant, this is a scalar constant, by a matrix and then transpose it, you could also transpose the matrix, then multiply by k, and you'll get it. And if you were to transpose the matrix and then transpose it a second time, you get back the original matrix. And these are, you can try them. You know, you could take a matrix and try it. I want to show you an example for every day. You're not smart children, right? Take a matrix, try what the people say. So we learn how to add, we learn how to multiply, we learn how to do scalar multiplication. We did all of this before, right? So you could actually make up a matrix and or two of them, because you need A and B, you need two of them, and try them. Well, they're doing an example for you here, right? So add the matrices, then you transpose. Add them, right? Equal to this, and then you transpose, right? Now, in the second instance, you transpose this matrix, you get this, you transpose this one, you get that. When you add them, these two matrices are the same. See? So here, they're doing this piece here. Add them together, get this, and then you transpose it, right? When they put a T in it, transpose, and you get this. So this part here, add the transpose of the individual matrices, right? You transpose that together, transpose this together, and then you add them together, you get this. Or you know, these two are the same thing, right? We cannot do every one of the properties because we're going to have a very, very long video. And no work for you to do. So you're not using your brain, right? You got to use your brain energy. Your brain to develop, you got to use it like a muscle, right? Similarly with this one. What's happening here? So AB transpose, right? So you take A, okay, they're assuming this is A, this is B, multiply, and you get that, right? And you transpose it, you get that, right? So notice here, you could put A, B, because you can't multiply this matrix by this matrix. You can multiply this matrix by this one, so you have to switch it around, right? The transpose of B, that's this matrix in this. Transpose of A, that's this matrix in this. When you multiply them together, and they are equal. Right, so I think that might be the last one you're going to show. All the properties, you can test them out on it. Well, this is not so useful when it comes to the inversion of matrices. So try just at one of the types. I think this belongs in the previous video where we talked about types. Right? But I guess because it dealt with transposing a matrix, they put it in, right? So if two matrices, when you transpose them, they're the same matrix. You call them a symmetric matrix. And they're telling you here that when you do the transposition, the diagonal elements are not affected. Right? Here. These here, we transpose what happens. A remains where A is, B remains where B was. And the little properties, you know, they want to remain. So now we talk about transpose. So they want to turn our attention to the inverse uh, formal, So basically what they're telling you, and I said this before, if two matrices multiply to give you the, what you call the identity matrix, well then one is an inverse of the other, right? That's what they say. We got it. So our aim then is to find the inverse. How do you find the inverse? The mathematics is very deep and heavy. I'm going to attach at the end of this video a number of examples I found on YouTube that does the inversion very, very. They didn't delve into the mathematics. In this video, I'm going to get into the mathematics a little. If you don't get it, you don't have to worry so much because that's it. You know what I was saying when we were doing financial maths. In mathematics, there will be deep mathematics behind financial mathematics is really heavy algebra. Have you ever thought where those formulas come from? You think I could show you all of that in this course? We would take about maybe a whole semester, maybe 2 semesters to just get those formulas that we use. So we're not going to get in deep into the math. We're going to skim it and surface. But the examples will really bring it up. When you watch the example, you say, man, sorry, I should have told you this. But these things are easy. You're going to see it's very simple. But you have to get head on. One little sign wrong, one determinant wrong. Everything goes wrong. Right? Thankfully, there are these softwares online that can help us. Right? And that's why matrices is so important. Because it takes the method, these, there's something called row operations. We're not going to talk about it. It is so systematic, it lends itself to programming. Right? And because it lends itself to programming, I'm talking about computer programming. People write code now, they write programs that will do everything that you want to do with a matrix. Just imagine. Right? So you want to check your answer, there it is. Right? I'll leave it to you to go search for programs of that sort. Good. So here it is, what they're talking about. If you take a matrix and it's inverse, you multiply the two, you'll get your unit matrix. I didn't show you how to find the inverse yet. We come into that. That is a little, or maybe if you wrote CXC, right? Most of you did CXC and you did, I think you were exposed to matrices a little, right? And no doubt, all of you know that to calculate the inverse, I think there's a thing where you put 1 over the determinant of the times what you call the adjoint matrix, right? You should actually write 1 over the determinant times the adjoint of E, right? Sometimes people write this in adjoint of E, right? Over this. Sometimes they read this as E adjoint rather than adjoint of E. It's E adjoint over the determinant. Right? But this here is this is an actual matrix, right? This is a matrix. This is a matrix. Right? That's why you don't see this plenty because you say, how do you put a matrix over a number? That is determinant is usually a number, right? But you can do it, you can do that. It means you're multiplying 1 over 8, which is a number. So always a horrible fraction. Not always, very often. And then you multiply the adjoint matrix by it, and you get the answer. In this case, the author find a nice matrix for some reason. Nice matrix, no fractions. I know you'll quarrel, man, so why ones you giving me full of fractions? And again, these are some properties. If you were to take two matrices, multiply them, then find the inverse, it's equal to the inverse of one multiplied by the inverse of the other. Notice the order was rearranged, just like with the transpose, right? Inverse of a matrix, if you invert it back, you will get back the matrix. That makes sense. This is interesting. The transpose, inverse of the transpose is equals to the transpose of the inverse. It's like you can swap around the powers, huh? And then if you multiply a matrix by a scalar constant, then find the inverse. It's equal to 1 over Q times the inverse of it. And these are all properties, again, if you were to do examples illustrating each one, well, you know what will happen with this, right? So you can probably test them out. When you learn, I mean, you have to learn how to find the inverse in the first place. Then when you found the inverse, maybe you can test all of it, right? It's good to know them. I can very well throw in some multiple choice based on them. Good. So now we're getting to another term you're going to hear in connection with the inverse. We talk about the transpose of a matrix. That is going to be useful. Now you might say, God, well, what I got to do with determinant? Maybe not, nothing at all. But when it comes to inverses, you're going to see how they're all connected together, right? So keep transposing them. Now we turn our attention to the determinant. Why this is forced is because, as the name suggests, it will determine whether the matrix has an inverse in the first place. Why do all the other things? Why find what we call it cofactor and, transpose it, and why do all of that if the thing doesn't have an inverse? Right? Keep that in mind. I remember, I'll tell you a quick story. Very, very long ago, not very long, but I'd say about 10 years. About 10 years ago, I had a friend who was teaching this exact course, right? And you wouldn't believe what this guy did to me. He knew that, I knew a little bit of mathematics. And in a test, this man, he saw a pseudocode problem. I don't know if you know what is a pseudocode. Pseudocode used to be in a newspaper. I don't know if they still have it. And he took the thing and brought it to me and said, I am not to do the final exam. I'm to do this thing for you in the test. I said, sir, what is the problem? How, suppose, you give me not the test, but I'm not doing the test, you give me something else. Only to figure out after 2 hours, the pseudocode problem he gave me, he tampered with it, he changed up some numbers, and it wasn't coming. And I told him, I said, man, I didn't do the test, so you don't do it. He gave me an A because I know that I can do anything, He gave me an A. He said, look, forget it. I'm the next one to do I want. Unfortunately, he died. I think I'll tell you how he died. They found him in his apartment at 6th Street here. 6th Street? No, 6th Street. They found him there. I don't want to give you more details. He died. Very brilliant guy. Very, very bright. He was doing his PhD. He come from Cuba and then. All right, yeah. So let's talk about the determinant, right? So here is your matrix, 1, 2, 6, 5. And they're telling you, well, this is how you write the determinant, right? This line like here, like a modulus line. I don't know if you know what's a modulus line from other mathematics, right? This is not the determinant. This is just a symbol, right? This thing on the side here. But I guess if you did CXC, you know how to find the determinant, right? It's this number by this number, subtract this number is. So it's 1 multiplied by 5 minus 6 multiplied by 2. And you get your answer as 5 minus 12, which is 7, right? You know that from CX, but with a little reasoning, we're going to get into it. I give you some trouble. How they come up with that idea that there is a deformity. There's a general formula so that led us to this shortcut. That's a shortcut we use there. That's not finding the formula. So this is what the first things you want to do. You want to find the determinant of the matrix. If the determinant is 0, remember in the matrix the inversion thing, you have to have 1 over the determinant times the adjoint of B, right? Now, if the determinant is 0, if this is 0, you will have 1 over 0, which is undefined. Therefore, the matrix doesn't have an inverse. So that's why the first thing you want to do, find the determinant. Because if you don't find it, you can be wasting time doing all the other parts, only to figure out the thing doesn't have an inverse. Good. So, well, this is going to sound like foreign language, right? So what they're actually telling me here, right? Basically, okay. Let's see if I can. If you have what you call a 1 by 1 matrix, 1 by 1, right? Or 2, right? So this is a matrix. 1 row, 1 column. They're saying when the determinant is 2. If you have a 2 by 2, if you have a 2 by 2, right? Let's say 1, 3, 2, 6. Right? Look at this. Well, then the determinant is going to be 1 plus 6 minus the 3 by 2, which is 0, right? So the determinant of 1, 3, 2, 6 equals 0. And you know that this matrix is a singular matrix. So you'll see how well as the matrix get a little bigger, 2 by 2, 3 by 3. How do we go about finding the determinant? Right? I think in mathematics too deep. I'm going to try to skip over as I go along. Because the shortcut process is what you have to use, right? Okay. Okay. Related to the determinant, what you call the minors of a matrix, right? The minors of a matrix. And each matrix, let's say, okay, let me speak of a minor. Let me give you a minor. You know, what do you mean by all of this right thing? So let me use this matrix. Let me use the matrix. Let me use the matrix 1, 3, 2, 6. Let's say I want to find the minor of this one. What I'll do, I'll cross all those numbers and leave those. So the minor of 1 is 6. So we can put 6 here. The minor of the 3, cross all this and that, it will be 2. 2 there. The minor of this 2, cross out here and here, and it will be 3 here. And the minor of 6, I'm gonna cross out this and that, and you will get 1, right? So this is your um, the minors all assembled into the minors of each element of this previous matrix. They're all assembled into a matrix here. There's a sign convention um, that is associated with each cofactor, right? Uh, just now you see it, something called cofactors, right? So you will start with a plus here, then a minus, then a minus, then a plus, right? So this rule starts with plus, minus, and it goes on like that. This one starts with a minus, plus. Now, if you were to take the transpose of this, right? Look at what you get 6 minus 2 minus 3, 1. Right? And this is what they tell you in high school because the original matrix was 1, 3, 2, 6. And the adjoint matrix, what you normally switch this around, right? The 6 goes there, the 1 comes here. That's what you see happening here. And you notice there's 3 here and 2 here. They tell you change the sign on these 2, right? And you see what they're minus 3, minus 2. Right? So they don't tell you that, all this thing about minor and cofactor. They don't tell you all of that. They just give you the shortcut. And that's what you'll be expected to do when you are asked to find, well, eventually the inverse of a matrix, right? You don't have to do this step by step thing that I'm doing. I'm just trying to explain all this writing, what they really mean when we talk about the minor, right? So the minor, let's say, let's go back that. You have 1, 3, 2, 6. The minor of this number, you cross out the column that it's in, and the row, and the minor matrix of 1 is in the matrix 6. And the determinant of the matrix that is just has an element 6 is 6. Right? And that's why you put you put 6 here, 6 here originally. What the sign that goes in front is this determined by something else. There's something called a cofactor. And there's a certain sign that you put in front. You see it in the rest. Right? And you go on like that. You find the minor of 3, the minor of 2, the minor of 6. And you get all these in 6, 2, 3, 1. Sign in front. So you talk about how you get that adjustment. Right? I was just showing you when you get what you call it cofactor matrix, right? So you have all the cofactors. Right? Which you get from the minors, right? And then you have to add on a sign to it. You get this. Transpose that and you get this. Right? And that's what they tell you in high school is the adjoint of the original matrix that we have. Right? And I hope they won't lose you there. So here is how you actually get the minor and then find the determinant of that minor matrix or the submatrix, right? So, like if you want, what's the submatrix of this force element? Draw through a line here, draw through a line here, and this matrix is there. That's what they have, right? You find the determinant of it. That's what they call the minor, right? As I said, you see in textbook where they call that little matrix the minor matrix. And the minor is actually the determinant of the minor. You see the term is like variance. And you have to do that for, well, to find the determinant, you have to do it for an entire row. Right? So let me do it with the second term, right? So let's see, second element. Right, let's see this one, right? Draw a tristle, draw a tristle. And your minor will be the determinant of A21, A23, A31, A33. Right? And these will be numbers. So you just multiply this by this minus this by this. Right? That will be all. And similarly, if I'm to go to the third one, let's say this one. Okay. Draw through here and row in the column. And this here is your submatrix that you calculate with your minus one. Right? How you do that, you just multiply this by this minus that by. Right? Good. And from all of that now, you have to get something called the cofactor and so on. Then you calculate the determinant. Right? You come to that. So they're showing you all the other things. This is what I just showed. Cofactors. This is what the next thing is. What are you talking about here as a cofactor? The cofactor of every element. The cofactor of every element of a matrix is this. Notice this is the minor there. You have to find the minor. Right? Right? Just how to find the minor. And there is a sign attached to it. Notice it's -1. And the power is, notice what is the subscript under here? IJ, this sum the subscript. Right? And that will show you that usually, if you were to find the cofactor of, notice, first element in the first row, the second element in the second row, and the third element in the third row. What am I saying? First element in the fourth row, the second element in the fourth row, and the third element in the third. What you want to notice here is the sign plus, minus, plus. If you were to go to the second row, right, you'll see 2, 1, C, 2, 2, C, 2, 3. And if you were to add these up, 2 and 1, you'll get 3, right? To add these up, 4 and 5. If you were to raise -1 to the third power, you get negative. If you were to raise -1 to the fourth power, you get a positive. And you were to raise -1 to a fifth power, you get negative. So in the second row, so your cofactor matrix will have, for this here, plus, minus, plus. And in the second row, you have minus, plus, minus. And in the third row, you have plus, minus. Right? That's all. For bigger matrices, you continue the trend. You'll just continue the trend. You know? I notice like okay, plus, minus, plus, it comes on here. After plus is a minus. After this minus is a plus, and so on. You'll see all of it when you see the example. I know, wow, what the hell is going on here now, this cofactor, this sign, this. So each element of the cofactor matrix, it has to have a sign in front. Usually it varies like this, plus, minus, plus, minus, plus, minus, plus, minus, plus. Okay, and then determine whatever the number you have here is a negative, sorry, a positive, that's no problem. But if the number itself is a negative, that negative and this negative become positive. Don't think that the cofactor matrix has to have a positive followed by a negative number, followed by a positive number. Don't think so. This is that you put in front of the number. Maybe you have a negative already here, and then you put a negative sign. The two negatives become a positive, right? All those are possibilities. That's what I'm saying in mathematics, a little too heavy. So you're gonna, when you follow the examples, you'll see it's much easier, right? It's much easier. Now, how do you find the determinant now? Right? How do you find the determinant? So notice what they tell you you're doing here. And again, the mathematical language here is very complicated, right? Notice they're telling you. To find the determinant, you take one rule. Just take a rule. You take rule 1, rule 2, rule 3, whatever. Notice you're taking the first element by the cofactor of that first element. The second element by the cofactor of the second element, and so on. Right? You just have 3, you have third element by the cofactor of the third element. Right? All of this seem too mathematical. An example will better illustrate it. Better example, don't worry. Right? And here they're going down to if you have 2 matrices, right? 2 by 2 matrices. But this is very simple. You have a 2 by 2 matrix, right? So basically, they're telling you, okay, the cofactor of this matrix, this element is this. That's this number here. Right? Cofactor of this one is this here, right? 4 turns out to be that. Right? Minus. So what I said we do to find the determinant? Take first term A11 times this here, which is that. Right? So A11 by C1 plus A12 by C1, which turns out to be this and this and this. It's A11 times A22 minus, notice where this minus comes from. The minus comes from this side. Right? So that's how you get your determinant. And it boils down to what? It boils down to the shortcut. You don't have to know this mathematics. It boils down to it boils down to this number multiplied by this number minus this number multiplied by that. Very easy. You don't even have to know about shortcut. You multiply this number by this number minus this number by this. Simple as that. But it's good to know, as I said, I think I'm going to skip over most of the mathematics. What I'm doing here. I did say I'm going to do that. Right? Simple example. 3 by 2 minus 1 by 1. Look how this is. I need to skip over the heavy mathematics. Right? This is not easy. This is CX. 3 by 2 minus 1 by 1 gives you 5. That's your determinant. And well, if you have a 3 by 3 matrix, that's what they're explaining to you here, right? If you're taking the cofactors, they're fine. So what's the cofactor of what's the cofactor of this one? Cross out here, cross out here. And you take this matrix, finding the determinant of it, which is this multiplied by that minus that. And the sign in front is positive. The reason why is that it's sum of 1 and 1. 1 plus 1 is 2. So minus 1 to the second power is positive 1. So there's a positive sign. In the second case, notice we want the cofactor of this one, at this company. Right? So you cross out that and that, and you take this number, this number, this number, that number. That's what you see there. Notice the sign in front is a minus. The reason why is there is 1 and 2 subscript here is 1 plus 2 is 3. So minus 1 4th power equal minus 3. That's why you get a minus sign here, you have a minus sign. See? And so on. Again, let me do one with a number inside. The numbers inside. Now, I hope it's so. We have one. Let me see, we have one. The one is I find one with the numbers inside. Okay, look at this one. Right? So we take the 1. We take the 1. put it here. Then you find the determinant of this piece. Right? 2 by 1 minus 3 by 0. Right? That's that. See that? Okay. Let me erase and I'll do the second. Okay. Then second number is 0. That's what you see here. You don't even have to do nothing because it will become 0 anyway. Right? So you don't have to do anything. But where you got is 0 and 2. Take this, you take that. Then you're left with 0, 1, 3, minus 1. 0 by 1, 0, minus 3 by minus 1. This 3 by minus 1 will give you minus 3. So minus 3 becomes positive. But you don't need to do none of this because this number is already 0. So this whole thing will become 0. Right? Similarly, okay. Go to this last one here. Cross out this row and column that is associated with it. Look at this. Right? So, oh, notice the sign, right? We got plus. Here is a minus. And then we go back to a plus, right? I didn't mention it. So this one you put here times 0 by 0, 0, minus 2 by minus 1. So the 2 minus it will become a plus. And you simplify all of this. Yeah. I am going to include a video from YouTube where there's a shortcut to find the determinant. Right? There's a shortcut where you take, I think it's these two rows and you put it in the back. Do some multiplication this way, minus some multiplication that way. We'll see that. It's one of the figures. It's a shortcut that somebody figured out. Now, the next thing is finding the adjoint matrix. And the adjoint matrix is really the transpose of the cofactor. The cofactor matrix. Right? That's why remember we started out talking about the transpose. And you want to know what am I going to do? Right? So the cofactor of this matrix is this. But then you have to transpose this. Right? If you were to transpose this, you will get, the 4 trillion minus 2, right? 4 trillion. Yeah. So you really remember from CXC again, what happened here? Is that you switch around 4 and 1. That's what happened here, 4 and 1. And I changed the sign. This was positive 2, you have minus. This was negative 3, you have positive. See? So your adjoint matrix is the transpose of the cofactor matrix. So after you found the cofactor matrix, right? You actually find the transpose, and that's your adjoint. And remember, we are closer now to the inverse. Inverse is 1 over the determinant times, the right word, adjoint. Adjoint of E, right? The adjoint of E. So we learn how to find the determinant. You also learn how to find the cofactor matrix. And then take that and transpose it, and you get the adjoint. We're going to see all of it in an example. Right, so that's what they're telling you. The adjoint matrix is the transpose of the cofactor. So here we are, the determinant is 10. Right, how you get 10? 1 by 4 minus 2 by minus 2 will give you 10. right? And they told you the cofactor in the previous slide when you transpose it, and that's what it is. Switch around 1 on the 4, change the sign. Right? Um, well, you remember they told you that A times the adjoint and the adjoint times A will give you the same answer, right? Do you notice that when you multiply these two, you get 10 times the unit matrix? And it so happens that this number in front here, usually, this is something I'm yet to test. It's really the determinant. I mean, that's a good exercise to try to see when you take the matrix and its adjoint, if you get that determinant in front of you. I think I have to try it out, prove it to myself. Right? And we go right back to what we talked about, right? That the matrix and its inverse must multiply to give you I, right? And therefore, okay, A times the adjoint equals to the adjoint times B, which is equals to the, what is this? The determinant times I. So basically, the inverse then is equals to the adjoint of B over the determinant of B. Right? Okay, use that idea and see if you have a. This is 2 by 2 matrix. I don't want to. 2 by 2 is too easy. Right? This is too easy. I will go to 3 by 3. Okay, look at this one. Yes. Right? Cool. So here's a 3 by 3 matrix. As I said, I'm going to attach a few videos to this video. It will be very lengthy, I'm sorry. So you're going to have like how to find the determinant, uh, what else? How to find the inverse. I'm going to put on some examples. So you're going to see some more. And then during the tutorial session, I'm going to do maybe an example or two, right? Because even though it's an hour, two inverses will take us that whole 1 hour, right? So we start off with the determinant, right? We have the matrix. We want to find the determinant before we shouldn't be wasting our time doing any other thing, right? So we start off, we take this element, put it in front here, times, we cross out that, find this determinant, which is 1 by minus 1 minus 2 by 0, which is minus 1 minus 0. So we get that. Going to the second element of the function. So you go here, this one. Cross out this, cross out that. Right? So put that 1, notice here. Oh, is it 1 or minus? Oh, the minus 1 here. Okay. There's a minus 1, then across. Good. So notice, remember, we have to start with a plus, a minus, and that's why you see a minus sign. Minus and then a plus in there, right? But then, even though this is a minus, this number here is minus 1 by itself. You know what might happen here, right? And then you find the determinant of this piece of 2 by minus 1 minus 2 minus 1 by 0, which is 0. Right? Notice that looks a very confusing thing. So you have a minus and another minus and then another minus. It might end up with a minus sign eventually. Right? Yes, I did see that. Okay. There. So we got 3 in the beginning. Then we have minus 7. That's from this piece here. Is that right? No, no. So we're doing another calculation. We're sticking to this portion. So, and then let's go to the tutorial. Let's go to the tutorial. So taking this number, cross out this, cross out that. This element is 1. And this here is what? 2 by 2 is 4 minus 1 by 1 is 1. You simplify all of this and get minus 2, which tells you the matrix does have an index. Right? What you have to do next, right, is you have to take every element inside this thing here and repeat this cofactor thing, right? So notice what was done here, right? A lot of work now. A lot of work. So you take this tree, right? Cross it out, right? And look what 1 by minus 1, right? You get minus 1. Minus 1, that will be 0. You get minus 1 again. So repeat that procedure for this element, you get that. Repeat, let's do it 1 by 1 so that we can see that. It's a lot of work. So let's go to the second one, right? So go to the second one. Take this one, take it out, right? 2 by minus 1 and minus 2. You're supposed to subtract 0 by 1, but 0 by 1 is 0. But 2 by minus 1 gives you this minus 2. But remember, in the cofactor formula, start at plus, then you get a minus. Right? Then you get a plus back again. So let's see the way that is 3 for me. So cross out. Okay, this third one is going here, here. And we find the determinant of this. 2 by 2 is 4, 4 minus 1, 3. That's a negative 3. Right? What's this and what is this? I'll repeat that same procedure. I know it's a lot of work. Right? We go into the second row now. Right? So second row from there, starting this one. You cross out this and this. Remember the cofactors in the second row has to start with a minus, then a plus, then a minus. What about these numbers in here? That's it. So minus 1 by minus 1 is positive 1. Minus 2 by this 1 is 2. So that's positive 1 minus 2 gives you minus 1. That's where you got this. Right? For you. A lot of work, a lot of work. Then we go to the second one here. That means we'll cross. So this one, right? The sign is going to be plus. 3 by minus 1 is minus 3. Minus 1 by 1. This will become minus 4. That's where we got that. Right? I'll do the last one. I wouldn't go to the term. By now you're probably saying, when this man was done, I'll go to the tournament. Right, that this one. This one. Cross over here and here. Right? And remember that sign has to be a negative, right? So 3 by 2 is 6. Minus 1 by minus 1 minus 1. So 2 minus is become a plus. You get 7. That's what we got at 7. And you repeat the same thing to the term, each element here. And that's where we are these. When you take all those together, take all the cofactor matrix. Cofactor matrix will look like this. Minus 1, 2, 3, 1, minus 4, minus 7, minus 1, 2, 5. Right? So your cofactor matrix is. So your adjoint, the adjoint of A will be the transpose of this one, which I would think they did on the next slide. So I'm just taking all these numbers and putting it in the cofactor matrix. You're probably saying, why the diagram on the drop on this course? Cool. So you have the cofactor matrix, and you simply transpose it to get the adjoint matrix, right? So notice here, you take this row, you put it here, you take this row, you put it here, you take this row, you put it here. And that's your adjoint. Right? We found the determinant order to be -2. So 1 over -2 times this matrix here. And this is your inverse of E. Right? So that's a lot of work. Here. As I said, I'm going to attach to the end of these slides here, right? This video, sorry. Some videos I pulled out from YouTube. And if you go searching, you might get searching all over here. You won't be able to find it. So I'm going to attach it so that you can learn how to find the determinant and then learn how to find the inverse. Right? I think afterwards, you have quite a number of these are 2x2 matrices. Right? So remember we said that if the matrix is singular, that is, it doesn't have a determinant, not it doesn't have a determinant, the determinant is 0. If it's not 0, well then yes, you have an inverse. Right? I'm not going to waste time on the mathematics behind the 2x2 case, right? I'm just going to skip it away. I'm going to end my part here. And at the end here, I'm going to attach those videos that I promised you. After this is the mathematics of the whole thing, you know, a whole set of mathematics that's kind of deep and you might not get a full appreciation of it, you know. They want to show you how is it they come up with that formula they give you in high school, right? They want to show you how did they come up with that formula. That this is the inverse matrix, you know. Yeah, I'm not going to waste time. This is an example. Right? And then in high school too, no doubt, they show you how to find the inverse and use it to solve equations, right? And I think they showed you this. That if A times X, where A is really the matrix made up of the it's made up of the coefficients of, well, in high school you probably had X, Y. In higher education, something they put X, Y, and Z. Here they have X1, subscript 1, X2, X3, and so on, right? Yes, and once you know that, to find X, you just take the A over. Let me just tell you what I'm trying to do. If you write the coefficients as a matrix, these are the coefficients of the equation, right? Coefficients of X1, X2, X3, and so on, right? Times X is equals to B. So if you were to, let's say you have an equation, I'm just showing a point. X plus Y plus Z equals 4, 2X plus 3Y, 3Y minus Z equals 6. X plus Y plus 2Z equals 10. Let's just say that. You can take this here and make it into a product of two matrices. 1, 1, 1, 2, 3 minus 1, 1, 1, 2 times X, Y, and Z. If you multiply these two, you will get back this. All of this is equals to 4, 6, 10. Right? they're telling you here that, okay, this is like A, this is like B, sorry, this is like X, and that is like B. So X then, if AX equal B, then X will be equal to A inverse B. So your big trouble is to find A inverse, which is the inverse of that. Right? That's your biggest worry. And once you find that, remember, if you take your inverse multiplied by B, that will give you X. Right? So they're taking this and say X is equals A inverse B. So once you find A inverse, you multiply by B, and you will get your X here. Right? And that's what you see here. That's what you're telling me. That's what you're telling me. Right? Let me see. I think they did an example. So here you have three equations. Notice they didn't use X, Y, and Z. They use X subscript 1, X subscript 2, X subscript 3, right? You take these and you decompose it into these two matrices. Right? And then you take the 2, the 1, the 3, put it over. So this is like AX equal B. So as I said, X will be equal to A inverse B. The big trouble is to find the inverse, right, of that. I think they didn't actually show you the step, they just state it. So that's the inverse, right? Find the inverse, multiply it by B, and you will get X1, X2, X3. And this is, they're just checking the answer. They're just checking it out. Good. So I'll stop here. And as I said, I'm going to attach some videos to the end here that will kind of give you some more worked examples, you know, that will help you. And then in the tutorial, we'll do a couple of minutes. All right, so that should, by the end of it, you should be able to catch it.
In this video, we're going to focus on finding the determinant of a 2x2 matrix and also of a 3x3 matrix. So let's start with the basics, the 2x2 matrix. Here, let's say this is A, C, B, and D. So it's going to be equal to A times D minus B times C. That's how you can find the determinant of a 2x2 matrix. So let's work on some examples. Let's say if this is 3, 5, negative 4, 7. So it's going to be 3 times 7 minus 5 times negative 4. 3 times 7 is 21. Negative 5 times negative 4 is positive 20. And when you add them, this will give you 41. Now it's your turn. For the sake of practice, try this one. Negative 7, 8, 4, negative 3. So it's going to be negative 7 times negative 3, and then minus 4 times 8. Negative 7 times negative 3, that's 21. Negative 4 times 8 is negative 32. 21 minus 32 is negative 11. So that's how you can find the determinant of a 2x2 matrix. Now what about a 3x3 matrix? So let's say this is A1, A2, A3, and then B1, B2, B3, C1, C2, C3. So let's go over the formula first. The first thing you want to do is get rid of the first row and the first column. And notice what you have left over. B2, C2, B3, C3. So you're going to use A1, and it's going to be reduced to a 2 by 2 matrix. So it's going to be A1, and then B2, C2, B3, C3. So when you cross out row 1 and column 1, you'll be left with B2, C2, B3, C3. Now let's move on to the next one. So it's going to be minus. So instead of using A1, we're going to use B1. B1 is in the first row and the second column. So what's left over is A2, A3, and C2, C3. That's going to be in the next 2 by 2 matrix. So it's going to be negative B1, and then A2, A3, C2, C3. And then plus, the next one is going to be C1. C1 is in row 1, column 3. So what we have left over is A2, B2, A3, B3. So it's going to be C1, A2, A3, B2, B3. And then you know how to evaluate a 2 by 2 matrix because we covered that already. So now let's work on an example. So let's say we have 2, 4, negative 3, 5, 7, 6, negative 8, 1, and 9. So feel free to pause the video and work on this example. So we're going to use 2 first. So it's going to be, we're going to put the 2 in front. And once we use the 2, we need to get rid of row 1 and column 1. So we're going to use 7, 6, 1, 9. So that's going to be inside the 2 by 2 matrix. And then minus. Now we're going to use the 4. And we're going to get rid of row 1, column 2. So we're going to have 5, negative 8, and 6, 9. So it's a minus 4. And then 5, negative 8, 6, 9. Now the next number that we have is negative 3. So we're going to get rid of row 1 and column 3. So we have a negative 3 on the front. And then we're going to write what we see here. 5, 7, negative 8, 1. So that's how you can simplify the 3 by 3 matrix into 3 2 by 2 matrices, or matrices. Now let's evaluate this 2 by 2 matrix. So it's 2, and then it's going to be 7 times 9 minus 1 times 6. So multiply these two first, 7 and 9, and then minus 1 times 6. The next one's going to be 5 times 9 minus negative 8 times 6. So first we have a negative 4, and then 5 times 9 minus 6 times negative 8. And then we're going to have negative 3 times 5 times 1, which is 5, minus negative 8 times 7, which is negative 56. So 7 times 9 is 63. 1 times 6 is 6. 5 times 9 is 45. Negative 6 times negative 8, that's positive 48. And then we have 5 minus negative 56, which is like 5 plus 56, so that's 61. 63 minus 6, that's 57. 45 plus 48, that's going to be 93. Negative 3 times 61 is negative 183. 2 times 57, that's 114. And 4 times 93, that's 372. Minus 183. So if we go ahead and combine these last three numbers, this is going to give us negative 441. So that's going to be the determinant of the 3 by 3 matrix. Let's go ahead and work on another example. Let's say this is 5, 7, negative 8, 4, negative 3, 6, 1, 7, and negative 9. Go ahead and calculate the determinant of this 3 by 3 matrix. So the first number is going to be 5. And if we get rid of the first row in the first column, we're going to get negative 3, 6, 7, negative 9. Next, we're going to use the 7. So if we take away the first row in the second column, it's going to be 4, 1, and 6, negative 9. And then the last one, negative 8. So if we take away row 1, column 3, we're left with 4, negative 3, 1, 7. Now let's go ahead and evaluate the 2 by 2 matrices. So first we have negative 3 times negative 9, which is positive 27, and then minus 7 times 6, which is 42. And then it's going to be negative 7 times 4 times negative 9, that's negative 36, minus 6 times 1, which is 6. And then this is going to be minus 8. 4 times 7 is 28. And then 1 times negative 3 is going to be minus negative 3. 27 minus 42, that's negative 15. Negative 36 minus 6 is negative 42. And 28 minus negative 3, that's 28 plus 3, that's 31. 5 times negative 15 is negative 75. Negative 7 times negative 42, that's positive 294. And 8 times 31, that's negative 248. So if we combine these three numbers, this is going to give us negative 29 as our final answer. So that's the determinant of the 3 by 3 matrix. By the way, if you want to get more videos on algebra, trigonometry, pre-calculus, physics, general chemistry, organic chemistry, if you want to find more videos on these topics, feel free to check out my playlist. Or you could subscribe to my channel and get more information on this. At my channel, you could find like playlists on these types of videos, so you could search for whatever topic you need help in. So that's it for this video. Thanks for watching, and have a great day. In this lesson, we're going to talk about how to find the determinant of a 3 by 3 matrix, but we're going to do it using a shortcut method, or the easy way. So to begin, we are going to write the first column of the matrix, 5, 2, negative 6, and then we're going to write the second column, 3, negative 5, 4, and then the third column, 7, 8, 9. And then let's write the first column, 5, 2, negative 6, and then the second column again. So what we're going to do is we're going to multiply the numbers in a diagonal, starting from the top left, going to the bottom right. So we're going to multiply 5, negative 5, 9, and then we're going to multiply those three numbers, and then those three numbers. We're going to add these three products and subtract it by the sum of these three products in this direction. So let's multiply these numbers first. 5 times 5 is 25. Now what's 25 times 9? If you have 9 quarters, how much money do you have? 9 quarters is 225. So 25 times 9 is 225. Now we have a negative sign, so this is going to be negative 225. Next, we have 3 times 8 times negative 6. 3 times 8 is 24. 24 times 6 is 144. We do have a negative sign, so it's going to be negative 144. And then we have 7 times 2 times 4. 2 times 4 is 8. 8 times 7 is 56. Now, starting from the bottom left, let's multiply those three numbers. 6 times 5 is 30, and 30 times 7. 3 times 7 is 21, so 30 times 7 is 210. Since we have two negative signs, it's going to be positive 210. And then 4 times 8 times 5. 4 times 5 is 20. 20 times 8. If you have 8 $20 bills, how much money do you have? 8 $20 bills is 160. And then finally, we have 9 times 2 times 3. 2 times 3 is 6. 6 times 9 is 54. So now let's add these three numbers. Negative 225 minus 144 plus 56. That's going to be negative 313. And then let's add those three numbers. So 210 plus 160 plus 54. That's 424. Negative 313 minus 424 is negative 737. So this is the answer. That is the value of the determinant of this 3x3 matrix. So that's how you could find it quickly using this shortcut method. Now, for the sake of practice, let's go ahead and work on another example. So feel free to pause the video if you want to try this problem. So in the first column, we have 8, negative 5, 7. In the second column, 4, 6, 9. And the last one, 3, negative 2, negative 8. So feel free to try this problem if you want to. So we're going to follow the same example. Let's begin by writing the first column, 8, negative 5, 7. And then the second column, 4, 6, 9. And then the third column, 3, negative 2, negative 8. Then we're going to write the first column, 8, negative 5, 7. And then the second column, 4, 6, 9. So let's multiply these three numbers starting from the top left. 8 times 6 times 8. Let's use a calculator for that. 8 times 6 is 48 times 8, that's 384. We have one negative sign, so it's going to be negative 384. Next, we have 4 times 2 times 7, but we have negative 2 though. So 4 times negative 2 is negative 8 times 7, that's negative 56. Three times negative 5 is negative 15 times 9. 15 times 9 is 135. But with the negative sign, it's going to be negative 135. And then 7 times 6 times 3. 7 times 6 is 42. 42 times 3. 4 times 3 is 12. 2 times 3 is 6. So it's going to be 126. Nine times 8 is 72. 72 times negative 2. If you double 72, it's 144. So we're going to have negative 144. And then 8 times 5, or negative 8 times negative 5, that's positive 40. 40 times 4. 4 times 4 is 16, so 40 times 4 is 160. So now let's do the math. Let's add those three numbers. Negative 384 plus negative 56, or just minus 56, minus 135. That's going to be negative 575. 126 minus 144 plus 160. That's going to be 142. Now, negative 575 minus 142 is negative 717. So this is the final answer. So that's the value of the determinant of this 3x3 matrix. So now you know the shortcut method to quickly get this answer. Now, I do have another video that shows the older method of getting this answer. It's basically a longer way of doing it. You can check out that video if you haven't seen it already. But I've used the exact same problems in this video as I did in the other video. So it's going to give you the same answers, but as you can see, this method is a lot simpler to work with. However, the older method is useful for those of you who want to get the determinant of a 4x4 matrix, because this method is designed to work for the 3x3 matrix. By the way, for those of you who want access to more math videos like algebra or other pre-calculus videos, feel free to check the links in the description section below. You're going to get access to my website, which has my playlist where you can access more videos like this on matrices and other related topics as well. In this video, we're going to talk about how to determine the inverse of a 3x3 matrix. So let's say if we have matrix A and it contains the elements 1, 2, negative 1, negative 2, 0, 1, 1, negative 1, and 0. So go ahead and determine the inverse of matrix A. So first, we need to rewrite this in the form of an augmented matrix with matrix A and the multiplicative identity of a 3x3 matrix. So here's matrix A. It's 1, 2, negative 1, and so forth. And the multiplicative identity matrix is going to be 1, 0, 0, 0, 1, 0, 0, 0, 1. So now here's what we need to do. We need to perform elementary row operations and basically take the left side and make it look like the right side. Now the operations that we apply to the left side, we have to apply to the right side. So the right side is going to change as a result. And whatever the result is on the right side, that is going to be the inverse of matrix A. So let's begin by turning this number into a 0. To do that, let's subtract row 1 by row 3. And let's apply the result to row 3. Now, row 1 is not going to change. So let's rewrite that. Row 2 is also not going to change as well. Now for row 3, it's going to be 1 minus 1, so that's 0. And then it's 2 minus negative 1, or 2 plus 1, which is 3. And then we're going to have negative 1 minus 0, so that's negative 1. And then 1 minus 0 is 1. 0 minus 0 is 0. And then 0 minus 1 is negative 1. So now what do you think we need to do next? How can we turn this negative 2 into a 0? What row operations do we need to apply to row 2 to do so? So we're going to say 2 times R1 plus R2. Let's do that. So we're changing row 2. Row 1 is going to stay the same. Row 3 will remain the same as well. So 2 times 1 plus negative 2, that's going to be 0. 2 times 2 plus 0, that's going to be 4. 2 times negative 1, which is negative 2 plus 1, that's negative 1. 2 times 1 plus 0 is going to be 2. 2 times 0 plus 1, that's 1. 2 times 0 plus 0 is 0. Now, let's turn that number into a 0. So, we need to apply the row operation to row 3. I'm going to multiply R2 by 3 because 3 times 4 is 12. And then I'm going to subtract it by 4 times R3 because negative 4 times 3 is negative 12. And they'll cancel to 0. So row 1 is going to stay the same. And let's rewrite row 2. So we're going to have 3 times 0 minus 4 times 0, which is 0. And then 3 times 4 minus 4 times 3, that's going to be 0 as well. And then 3 times negative 1, which is negative 3, minus 4 times negative 1, so we have negative 3 plus 4. That's going to equal to 1. And then 3 times 2 is 6, minus 4 times 1, so 6 minus 4 is 2. 3 times 1 minus 4 times 0, that's 3. And 3 times 0 minus 4 times negative 1 is 4. Now, what we need to do is turn this number into a 0. So that's going to be straightforward. We just got to add row 1 and row 3 to accomplish that. So let's rewrite rows 2 and 3. So it's going to be 1 plus 0, which is 1. And then 2 plus 0, that's 2. Negative 1 plus 1 is 0. And then 1 plus 2 is 3. And then 0 plus 3 is 3. And 0 plus 4 is 4. Now let's focus on that number. What row operations do we need to apply to row 2 in order to make it 0? All we need to do here now is add row 2 and row 3. So notice what's going to happen. So let's rewrite row 1. And let's rewrite row 3. So row 2 plus row 3. 0 plus 0 is 0. And then 4 plus 0 is 4. Negative 1 plus 1, that's going to be 0. And then we have 2 plus 2, which is 4. And 1 plus 3, that's 4. And then 0 plus 4 is also 4. Now, what we need to do at this point, wait, hold on. I didn't copy this correctly. This is supposed to be 1, 2, 0, and 3, 3, 4. So everything else should be fine at this point. This is what I should have right now. So at this point, we need to turn this number into a 0. So we need to apply the operation to row 1. So let's take 2 times R1 and subtract it by R2. So we're going to have 0, 0, 1, 2, 3, 4, and then 0, 4, 0, 4, 4, 4. Now we're going to take 2 times 1 minus 0, so that's going to stay 1. And then 2 times 2 minus 4, that is now 0. 2 times 0 minus 0 is 0. And then 2 times 3, which is 6, minus 4, that's 2. The next one's going to be the same. 2 times 4 is 8, minus 4 is 4. And one thing I do need to fix, 2 times 1 minus 0, that's supposed to be 2. And I have a 1 here, so let's fix that. Now, what we need to do is multiply the first row by 1/2, and the second row by 1/4. And that should give us what we need. So half of 2 is 1. And half of 4 is 2. 1/4 of 4 is 1. So all of these will be 1. And then the last one is not going to change. So notice that here we have the multiplicative identity matrix I3, and this side represents the inverse of matrix A, 1, 1, 2, 1, 1, 1, 2, 3, 4. Now to confirm that it's indeed the inverse, what we need to do is multiply matrix A by the inverse of A and show that it's equal to I3. So in other words, we need to take matrix A, which was 1, 2, negative 1, negative 2, 0, 1, 1, negative 1, 0, and multiply it by the inverse of that matrix, which is 1, 1, 2, 1, 1, 1, 2, 3, 4. And if this is the matrix of A, if we did it correctly, we should get this answer, 1, 0, 0, 0, 1, 0, 0, 0, 1. So let's find out if we did it correctly. So I'm going to put my answers in here. First, we need to take the first row and multiply it by the first column and add the products. So it's going to be 1 times 1. So we're multiplying these two first. And then it's going to be plus 2 times 1. That's these two. And then plus negative 1 times 2. So 1 times 1 is 1, 2 times 1 is 2, negative 1 times 2 is negative 2. These two cancel, and so we get 1. So we have the first entry. Now, let's multiply row 1 by column 2. So it's going to be 1 times 1 plus 2 times 1 plus negative 1 times 3. So this is 1 plus 2 minus 3. 1 plus 2 is 3. 3 minus 3 is 0. Now let's try row 1 by column 3. So that's 1 times 2 plus 2 times 1 plus negative 1 times 4. So this is 2, 2 minus 4. 2 plus 2 is 4. 4 minus 4 is 0. Now let's move on to row 2. And let's multiply it by column 1. So it's going to be negative 2 times 1 plus 0 times 1 plus 1 times 2. So this is negative 2 plus 0 plus 2. Negative 2 plus 2 is 0. Now let's take row 2 and multiply it by column 2. So it's going to be negative 2 times 1 plus 0 times 1 plus 1 times 3. So that's negative 2 plus 0 plus 3. Negative 2 plus 3 is 1. Now let's multiply row 2 by column 3. So negative 2 times 2 plus 0 times 1 plus 1 times 4. So this is going to be negative 4 plus 0 plus 4, which adds up to 0. Now, row 3 times column 1. Let's try that. So it's going to be 1 times 1 plus negative 1 times 1 plus 0 times 2. So it's 1 minus 1 plus 0, which is going to be 0. Next is going to be row 3 and then column 2. So this takes some time. I mean, it's pretty laborious, but that's how you can confirm it. So it's going to be 1 times 1 plus negative 1 times 1, and then 0 times 3. So this is 1 minus 1 plus 0, which is 0. And finally, the last one. It's going to be row 3 times column 3. So that's going to be 1 times 2 plus negative 1 times 1 plus 0 times 4. So it's 2 minus 1 plus 0. 2 minus 1 is 1. And so we do get the identity matrix. So that tells us that this is indeed the inverse of A. So now you know how to find the inverse of a 3 by 3 matrix. Thanks for watching.
Alright, in this video we're going to do an example of finding the inverse of a 3 by 3 matrix if one exists, and we're going to do this by using cofactors and determinants. So the first one we're going to do here, we'll find the inverse of this matrix 0, 0, 1, 2, negative 1, 3, 1, 1, 4. The first thing I'm going to do is find the determinant of A. And there's different notations for the determinant, either the absolute, it looks like the absolute value of A. I always saw it just written as DETA, so determinant of A. To get the determinant of this matrix, I'm going to expand along the first row. So it looks like we'll get 0 times negative 1, 3, 1, and 4, and then minus 0, and we'll have to multiply that by the determinant of, it looks like 2, 3, 1, and 4. And then we'll add 1 times, we'll have to take the determinant of 2, negative 1, and 1, 1. Well, the first one's 0, the second one's going to be 0. Then it looks like we have 1 times, let's see, we'll get 2 times 1, which is 2, minus 1 times negative 1, which will be plus 1. So it looks like we'll get 1 times 3, or we'll get the determinant to be 3. Okay, so that's one thing that's going to be, we'll have to use that here in a little bit. The next thing I'm going to do is go about finding, I'm going to basically use the cofactors. So the way we do that is, basically I look, well, at the first, if I cover up the first row and the first column, I'm going to be left with the numbers negative 1, 3, 1, and 4. So that's I'm going to calculate the determinant of that. I'm going to have to fill in some signs here in a second too, so I'll get to that in just a moment. Next, if we cover up the first row and the second column, it looks like we're going to be left with 2, 3, 1, and 4. So 2, 3, 1, and 4. And if we cover up the first row and the last column, we'll be left with the 2, negative 1, 1, and 1. So 2, negative 1, 1, and 1. Next, if we cover up the second row and the first column, we'll be left with 0, 1, and 1, 4. So 0, 1, 1, and 4. If we cover up the second row and the second column, we'll be left with, it looks like 0, 1, and 1 and 4. Let's see, if we look at, if we cover up the second row and the third column, it looks like we'll have 0, 0, and 1, 1. And lastly, if we cover up the third row and the first column, it looks like we'll be left with 0, 1, negative 1, and 3. If we cover up the third row and the second column, we'll be left with 0, 1, 2, 3. And then if we cover up the third row and the third column, we'll be left with 0, 0, 2, and negative 1. Okay. So we still have to put our signs in here as well. So it just alternates. Positive, negative, positive, negative, positive, negative, positive, negative, positive. Alright, so the next thing I'm going to do is actually calculate the values of all these determinants. So let's see, we would get negative 1, it looks like we would get negative 4 minus 3, that would be negative 7. We would get 8 minus 3. 8 minus 3 would be 5, but we have to use the minus sign out front, so we'll get negative 5. We'll get 2 minus negative 1, or 2 plus 1, which will be 3. 0 times 4 is 0 minus 1, so we'll get a negative 1 for the determinant, but we have to multiply that by the negative, so we'll get a positive 1. 0 times 4 is 0 minus 1, so we'll get a negative 1. And then what it looks like we'll just have 0 times, 0 minus 0, so we'll get a 0 there. 0 times 3 is 0 minus negative 1 will give us a positive 1. 0 times 3 is 0 minus 2, so we'll get a negative 2 for the determinant, but with the extra negative, it'll switch back to positive 2. 0 times negative 1 is 0, minus 2 times 0 is 0, but this time we've got, well, it doesn't really matter, we've got a positive, but who cares because we're getting 0 anyway. Okay, so the next thing we have to do is we're going to have to now do a little reflection. And what we do is we reflect things about the diagonal. So this is going to be the diagonal. Those numbers are going to stay right where they're at. Okay, so I'm not going to move those numbers at all. So let's see. I'm going to leave the negative 7, the negative 1, and the 0 alone. But then we reflect the other elements about the diagonal. So the 1 and the negative 5 are going to switch places. So I'm going to get a negative 5 and a positive 1. Let's see. The 1 and the positive 3 switch places. So I'm going to get a 3 in the bottom left and a 1 in the top right. And likewise, the 2 and the 0 are going to switch places. So my 2 is going to go up here, my 0 is going to go down here. The last thing I do is I take 1 over the determinant. Well, the determinant we found was 3. So I'm going to multiply every entry by 1/3, and this is now going to be our inverse matrix. So if we multiply everything by 1/3, it looks like we get negative 7/3. It looks like we'll get 1/3, 1/3, negative 5/3, negative 1/3, 2/3. We'll get 3 times 1/3, which is 1, and then we'll get zeros for our other entries. And we have now found our inverse matrix.
Hi guys, and welcome to this video. So today we'll be looking at how to find the inverse of a 3 by 3 matrix using the core factor method. So to use this method, there are some few things that you need to know. You need to know how to find the determinant of a 3 by 3. Also, you need to know how to transpose a matrix, because we'll be using those concepts in this procedure. Okay, so to start with, let's start by finding the determinant of this particular matrix. So to get the determinant, we know that we should insert a positive, negative, positive there like that. Then having done that, let's start computing our determinant. So the determinant of this matrix will be given by det A is equals to, so we start with -4, then we form a 2 by 2 matrix, which is formed of course by everything except what is in this row and this column, which is -1, 4, it's supposed to be +3 and -3, like this. Then we have negative there, so negative, like that. We create another 2 by 2, which is formed by 5, -2, 3, -3, like that. Then lastly, we have a +2 here. So that will be 5, -1, -2, and 4. So this will help us compute the determinant. So in case you don't know how to find the determinant of a 3 by 3, I've shared the link in the description. You can follow the link then to help you find the determinant of the 3 by 3. Okay. To continue from here, let's find the determinants of the 2 by 2 matrices that we have formed now. So this is what will happen. The determinant of A will be given by -4. 1 times -3, that's 3, minus 3 by 4, that's 12. So negative will give us a +6. 3, -3 times 5 is -15. -2 times 3 will give us a -6, then to become a +6, because we have to subtract the two products. Then plus 2. 4 times 5, that's 20, minus 2 times 1, that's a +2, like that. Okay, so the determinant is given by -4 here, like that. Then 3 minus 12 will give us -9, plus 6, this will give us -9 again. Then plus 2, this will give us 18. Okay, so let's continue with it. Determinant of A will be given by multiplying these two, we'll simply get 36 minus 6 times 9, this should give us 54. 2 times 18 should give us 36. Okay, then from there, let's just add what we have. So 36 plus 36, so let's just say determinant. So 36 plus 36, that's 72. 72 minus 54 should give us a +18. So the determinant of this 3 by 3 matrix is simply +18. Okay, so we'll come back to this determinant. Let's just proceed and find the cofactor. Okay, so let's go back to matrix A. Remember, we've just found the determinant so far. So now there's this sign rule that you need to know when creating cofactors. So the sign rule looks like this. If you have a 3 by 3, this is my 3 by 3 matrix. Whatever you have here is positive. What is here is negative. This is positive, negative, positive, negative, positive, negative, positive, like that. So I'll show you how this will come in play once we start creating the cofactors. Okay, so from there, we're going to create 2 by 2 matrices that we're going to use to find 2 by 2 determinants to get to the cofactor. So this is what is going to happen. I'm going to create a very big matrix this way. Okay, so I want to create something very big, something like that. Okay, like that. So I want to create 9 4 by 4 matrices. So that's the first one, the second one, third, fourth, fifth, like that. Some of them look small. Okay, so you see what will happen once we start replacing the intended values. So now, according to this one is positive, this one is negative, though it's too small. We'll make it bigger. This one is positive, this one is negative, positive, negative, positive, negative, positive, like that. Okay, So now we want to start filling in these 2 by 2 matrices with values from matrix A. So to start with, we'll start with this 4 here at this position, which is this position here. So everything in the row for 4 should be hidden, and everything in the column for 4 should be hidden. So the remaining 2 by 2 matrix is what should be put in the position for 4. So the remaining 2 by 2 matrix is simply -1 according to this, 3, 4, -3, like that. Then from there we move on to 6. So we hide the row and column for 6, like that. So we'll create a 2 by 2, which is 5, -2, 3, -3. Sorry about that space there. Then the last value in the first row is 2, so we hide the column for 2 as well as the row for 2, like that. So the 2 by 2 formed will be 5, -1, -2, and 4. I'm sure you get the idea now. So if we come to 5, this 5 here, which is at this position, we're going to hide its row as well as its column. So what's the 2 by 2 formed? So the 2 by 2 formed will simply be -6, 2, 4, and -3. If we come at this one, we hide this and this, we remain with -4, -2, 2, and -3. If we come here, position 3, we'll hide this and this, so you get -4, -6, -2, and 4. Then the last row now, so at this position 2, so this and this, we remain with -6, -1, 2, and 3. If we come at this position, so it's this and this, so -4, 5, 2, and 3. At this position to be this and this, leaving us with -4, -6, and not really -2, but 5 and -1. Okay. So now with these values, we can create the cofactors now. We're going to find the determinants at every position. So of course the determinant is by multiplying this minus that, then that will be giving us the determinant of each of these 2 by 2 matrices. Okay, so let's create the cofactors. So to start with, here we're going to get 3 minus 12. That's 3 minus 12 to give us -9. So at that position, we'll have -9. At this position, we'll have -15, plus 6, which is -9. So we'll get a -9, but there's a negative, hence it becomes +9. 5 times 4, that's 20. 20 minus 2. 20 minus 2 will give us 18. Okay. If we come at this position, -6 times 3, that's 18. So 18 minus 8 will be 10. Now there's a negative outside, so we have -10. 4 times 3, that's -12. -12 plus 4 should be -8. Okay. If we come here, 4 times 4, that's -16. -16 minus 12 should give us a -4. -4, there's another negative, so it will give us a +4, like that. Then at this position, we'll have -18. So -18 plus 2, which will give us -16, like that. Here we'll have -12 minus 10, which is -22. So there's a negative, meaning that it becomes +22, like that. Then -4 times -1 is 4. 4 plus 30 should give us 34, like that. Okay. So what we have here are the cofactors. So with these cofactors, what we're going to do is we are going to transpose this matrix. If we transpose this matrix, what we're going to get is the adjoint of A. So after finding your cofactors, we have to transpose it. So let's transpose. So transposing this matrix gives us the adjoint of A. So adjoint of A will be given by the transpose of this matrix, of course. So if you transpose this, we'll get negative 9, 9, 18, negative 10, negative 8, 4, negative 16, 22, 34. Okay, so this is our adjoint. So now we're going to use the adjoint as well as the inverse to find the adjoint and the determinant to find the inverse. Okay, so this is what we've achieved so far. We've managed to find the adjoint by using cofactors, transposing the cofactor, as well as the determinant that we found in the first step. So now that we have these two, we can proceed and find the inverse matrix. So the formula for the inverse is given by, so the inverse of A is equals to 1 over the determinant of A multiplied by the adjoint of A. So once you multiply these two, then you get the inverse. Okay, so let's do that. The inverse of A will be equals to 1 over, remember the determinant is 18? Then the adjoint, which is this matrix here, is negative 9, 9, 18, negative 10, negative 8, 4 there, negative 16, 22, and 34. That. So we can multiply everything inside the matrix with 1 over 18, or rather we can just divide by 18. It's the same thing. So the inverse will be given by, so negative 9 over 18, just write like this. Negative 9 over 18 is the same as negative half. 9 over 18 is the same as half. 18 over 18 is just 1. 10 over 18 you can be reduced to 5 over 9 if we divide by 2. So it will be negative 5 over 9. 8 over 18 is simply negative 4 over 9. 4 over 18 is simply 2 over 9. 16 over 18 will be 8 over 9, negative. 22 over 18 can be reduced to 11 over 9. Then 34 over 18 can also be reduced to 17 over 9, like that. So this is the inverse matrix by using the cofactor method. Of course, there are other methods you can use, like row operations, but this is how I use the cofactor method for finding the determinant, the inverse of a 3 by 3. Thank you.